showing you the Linux boot up process, but we won't do that right now. We'll finish talking about kernel modules. Oh, first I want to ask about the project and talk about labs real quick. So I'm starting to get much better questions about the project. It used to be that when I asked people about the project, they asked if I knew how to make Swift work, usually on Linux or Windows or something that wasn't a Mac. So I was, it's not a bad question necessarily, but it doesn't indicate a lot of progress on the project. So lately I've been starting to see questions more of the topic, how do I make my functions go into the structure so that I can pass the structure into the tester function and then have the tester look at it? Much better question. Well, at least in terms of showing progress on this thing. So let's just kind of briefly overview this again and hopefully kind of cover things that maybe got missed. Okay. So if we look at the tester.c, so tester.c has this function included called test. And of course, what you want to do is run this test function to test your bundle. So you have to make a bundle, and then you can test your bundle and see if the bundle is all working correctly. So there's no main in this file right here. There's just test, so you have to call test from some other file. So the solution.c here has just kind of an empty main. And so from this main, you want to call test somewhere in here. So your general plan here, make a bundle that works, call test, and see that it works. Okay, so that's really the major goals here. And so when you call test, you'll have some bundle, and you basically say test, close this name B. Then you'd say that. Something like that to go call this and run it on your bundle. So that's the general plan here. So when you're making a bundle, you just have to write the functions that go in your bundle. And you have a variety of options as far as where you write them. In the past, most people just write them up here in this file. You can write them in separate files, or they could be nested functions in main or all manner of other things. But it's simplest to just write a few of those, and you make a bundle and throw them in there and call test and see if your bundle works. As far as putting everything into the bundle, this is sort of modeled after the way a lot of the files work in the kernel. So if you look at user src and Linux source, it doesn't matter what version really. Is it not impact? It is impact. Maybe we should go out and under a software and have this look the same script for everybody else. Okay. So the I have a few versions on there, but before 9. Okay. So if we go into the file systems here, for example, at ext4, it's a pretty common one, and look at something with file operations. Okay, maybe file.c. Okay, so here's an example. We're taking a struct file operations, and we're populating with actual functions. And so you can use this syntax to make your bundle, or you can just make your bundle and then set each of the members to your functions. So the other way to do it here, and you can't do this in a global sense, and so that's maybe part of why it's done here, would have been to say that construct file operations, and so you can have it, that's the name for your struct, whatever you want to call it, and you can say fops dot llc equals ext4 llc. Okay, that kind of structure would work too, except that we're a global scope, we're not in a function. And so since we're not in a function, only this way works at this point in this program, and we couldn't do this. But if you're inside main in your program, you can either do this or you can do this. Either way works fine. Either way, these are the names of functions that are defined a little bit higher up. And so if we look just right up here, this one is ext4 underscore llc, which is actually the function here that we're attempting to store in this struct member llc. So you can use this kind of model. write your functions, and then store them all in your case, it'll be a bundle struct. And then once they're all in there, you just pass the bundle off to test. Okay. I can't save the change, and I don't think it would actually build with that change anyway. Okay. So looking at this project again. You push T on that. Okay. So that's the general plan for solution.c. Write your functions, make a bundle that includes the functions, and then pass it off to test. Okay. So some other questions I've been getting, like that. The type def. So a type def allows you to rename a type something else. And so let's play with a type def for a minute. Okay. Okay, so I call this file typedef.c. Okay, typedef. So let's go ahead and typedef something. So int frog. Okay, I think I should go with the name. Okay, frog x equals 10. Okay, see if that works. Okay, I'll pull this thing up here. I realize we're excluding Alex from this, which is exclusionary. Okay, so x is 10. So this is what typedef does. If you have a type that's already known, you say typedef, your type, and then what you want to call it. So now a frog is the same thing as an integer, and we can say frog x equals 10. Now, it's not very popular to retypedef things like basic types. In this case, it doesn't make a lot of sense to retypedef it. I suppose if you wanted to have some program and you're like, well, we're going to typedef int as frog because later we might want to run a 64-bit, so we might say like long int. And so now x is a different size, and we just changed it everywhere in our program. Now it's long int, and it will continue to refine. And probably shouldn't define it as double, but if later we're like, okay, we're going to compile a version of this program that uses less space. And since we don't use any integers that are higher than 255, and we don't ever use a -1, now frog is going to be an unsigned char that we reuse it. And you can see it's happy here. No problem there. So that's what typedef does. Is let you define some other name for some type, and so then you can change it throughout the whole thing if you ever wanted to do that. So if you think about C++ and template classes, it gives you a little bit of the same functionality here, the ability to define your own type and then say at some point later what that type is. But there's another common use for it. Suppose we have some struct up here. I'm going to say struct. And this is going to be a, I don't know, it's a struct things, and it's got a couple of things in it, int x and char b. Okay, so then down here we can say something like this, struct things, my things, and if we take a look at the kernel syntax for this, let's pull up the second kernel here. Source or whatever, and fs, and we're looking at ext4. I think it's file.c. Okay, see the way this works here? Construct file operation, something equals something. Okay. So like that. See the semicolon at the end of that? So we're going to do the same thing. Okay. Dot x equals 27. Dot b equals 42. Okay, so there we made a struct things that's called my things. X, my things, dot b. Okay, see what happens. Okay, expected what did I do there? Oh yeah, comments. Yeah. Okay. I'm glad I accidentally botched that one because it emphasized the fact that they're not semicolons. Okay. So we made a struct my things. But every time we want to talk about this type, we have to say struct things. And struct things is 2 words. It's kind of lengthy. And you can see how you might not want to say struct things all the time. So a common thing to do here is to say something like this. Type def struct things things. Okay. And then down here, we should just be able to call this a things. Okay. There we go. Works just fine. And now we're allowed to say that. See, if we comment this thing out here, comment that out, then this isn't going to build. See? It says error unknown type things. Yeah, it is unknown type. So when we type def it like that, then we can do this. So if you don't like typing struct, whatever the struct is over and over, then you can type def it. Now, type defing is controversial. I don't believe Linus likes type defing. We go and documentation, and it's called style something. Maybe it's not. Coding. Maybe it's capitalized differently. That's I. There it is. Code. Okay. Type def. Please don't use okay. It's a mistake to use type def for structures and pointers. So when you see this, VPST, you know what it could mean. Whereas if you have struct virtual container something, then you can tell what it is. There is definitely some opposition there, and you can read through his points. I partly put it in the assignment so you can see both ways and make up your mind what you like. So there's a number of, it's kind of a long opinion on this, and in certain cases it is okay. One of the things Linus is very against here is type defing things as pointers. And so notice in his example here, VPST is actually a pointer. And so one of his objections here is type defing something as a pointer obscures the fact that it is in fact a pointer, since it hides that star, and then the VPST is actually a pointer to something, whereas he didn't necessarily know that. It doesn't necessarily apply in our case, but yeah, there's arguments against it there. I'd recommend looking at both sides of all these things. The fact is, if you go work for a programming company, they will have made up their minds about this stuff, and they'll have their own coding style, and you'll be stuck with whatever they do.
Initially, it could probably be kind of alien because you're like, okay, wait a minute, you guys have aliased all kinds of stuff here. What are you doing?
Yeah, in some cases there's that sort of thing. In a lot of cases, I'd say most cases, there's extensive library support that's been built up in a company before you got there. For example, one of the places I worked at, when I worked for Logos Bible Software, they used JScript to do a lot of the rendering inside the product. They had an embedded Internet Explorer with for the rendering engine. Now, JScript was a pretty basic language. It didn't have stuff like multi-threading. So somebody had hacked together a multi-threading library to run on JScript. So then everything we ran was actually multi-threaded. But the first thing to do is try to understand the company's one-off multi-threading library for JScript. And so that kind of thing is very common. So sad to say, if you go work for a large company, you'll get a big paycheck, and you just have to look at it and be like, I don't care that the style doesn't agree with me. I know the other side's argument, and I will accept it for now. You see? But if you understand both arguments, both sides of the issue, then it's easier to be like, oh, well, I'm not sure I agree, but at least I understand why, you know?
So,
yeah.
One question. I usually use define. What is the difference between type def and define?
So define is a cut and paste replacement.
Yeah.
So if we said this, define struct thing, okay, define things, struct things. Okay, how about the first one? Is that gonna work? I think it might. Yeah, it works. Okay, so the difference is how you did it. So when you say struct things there and a define, the define goes through and whenever it finds things, it automatically does this like text replacement. The type def is aware that it's a type, and so it informs the compiler to a greater extent what's going on,
Okay.
as opposed to just doing a simple cut and replace, search and replace kind of thing.
Okay.
Yeah. But yeah, good question. You can accomplish a lot of things with define that there's a built-in, like a more appropriate mechanism for. So for example, if you're like, well, I just don't like closing braces, you can define it as something. Okay. Oh yeah, so that's type N. So other things that people ask me about this project or have asked about, and so that the type F for this one is in tester.h, right up there. And so after that, we can refer to a bundle struct as a bundle. So you can say int test bundle star. Okay. Oh yeah. So if you look in the tester.c, a number of people have gotten hung up on this fill macro and returners and the nature of returners. So the nature of the returners here, basically, this is a address of a list of functions. So whatever you get, it'll be a pointer, and the length of this will be set by the parameter right there on find best, the last one that tells you how many items are in that array. So however many this is, the distance there is that third argument. So the length. I think on find best, well, I don't ever even named. Anyway, this is the third parameter. Okay. So what you get is the first parameter is this address. That's the first parameter. So each of these things here, the size, since we're on 64-bit, this will be 8 bytes. So that's the size of each of these entries in here. In this example here, you're getting 10 of them, but don't hard code in a 10. Whatever this parameter is what you get. I didn't test it with 2 different length lists. Okay, and the middle one, the second one, is the argument you give these, because each of these is the address of a function. And so each of these will point somewhere else to some kind of function. And that's what you want to run. And so shouldn't necessarily assume functions are contiguous in memory. But each of these points to some kind of function, and it takes as its parameter this second argument. So the second argument goes there. And so that's the one that's here. So you have to be careful to pass that in. So the main trick here is just, casting and making this stuff work correctly. So once you got the address of the first item in here, you should be able to figure out which one you're after here and cast it to an appropriate type and then call that function. You're just trying to figure out which one returns the highest number. So that's kind of a CS111 sort of algorithm, just find the maximum. Well, of course, what you want is not the maximum value, but the index of the maximum. So remember to track the index of where you found the maximum at 2, so you can return the right number. Okay, so the macro here, just fill returners at some position and 10. It takes this whole thing up here, so fill y and x. Y is that, x is that, the number there. And so it makes one of these pop out. And basically it's a little nested function here. And so the it takes a parameter there, x, and it returns 10,000 minus, so x as in its parameter, minus capital X as in that thing there, so 10 for the first one, times, so then again, the x there minus the capital X, that one, and then at the end turns, y equals, and then that was kind of the end of your function there. So y is what goes under returners right here. So the r pound x here, the name of the function has r double pound followed by a number. And so the functions actually have a number in their name. So when we say y equals the function's name here, we're populating this array. So this fill expands into two things. It's got the definition of your function, R, versus X, and it also adds it onto that array. Stores in that location. Okay, so yes, that's how that works. Now, looking at this, you might say, wait a minute, couldn't you have done a loop here? You guys had 10 of these things in a row. Well, there's a problem with that actually. That's that the loop is run when the program runs. The preprocessor, on the other hand, is going to run this fill macro before the program runs. In fact, before it's even compiled. So if it hasn't even been compiled yet, the loop surely hasn't run. I think there might be a way to write a loop in the preprocessor. I haven't looked into it very much. There may be a way to write a preprocessor loop to make that happen. I haven't been that interested in it. Okay, so that's what that part does. So then on find best, you can see how this stuff works on the inside, and you can write your find best function. Occasionally I got the question about sorted copy. How does what's it have to do to copy it? You just allocate space with malloc and then copy everything over. You can copy everything over just one at a time. That works fine. You can make a loop to do it. It'll be real short. There's also the memcopy function that copies memory areas for you. So if you really want a library function to do it, memcopy would be a decent plan. Remember to allocate your space before you call memcopy. If you give it a destination that's not allocated yet, it won't allocate it for you. It'll try to copy it there and cause a problem. Okay, you can kind of see that would happen because if you look at this, this is a void star, and so if you pass it the address of the memory area, it's got to use what you passed it. It can't change the parameter there. It's not passed by reference. It's not a double star. And so it's stuck with the area that you told it that it put stuff. Okay, the main way you get in trouble with this function is not making dest big enough. So dest needs to be about the size of the source, and that'll work. At least as much data as you have in the source. Of course, you can have a source that's bigger and only copy part of it out. That's certainly allowed. And N there does specify how much it copies. So this is not like strcpy. You're used to using strcpy and strncpy. strncpy lets you specify an end of your copy, so you're going to only copy up to n bytes, but it will stop on a null termination. So really the main difference between a memcopy and an strcpy or strncpy is these functions stop on a null terminator for a string, and memcopy does not. So for this project here, where you're copying this list of numbers, you can't use strcpy. First of all, there's a 0 in here, and that's a null, and so that would stop strcpy. But secondly, and perhaps less obvious, these are 32-bit numbers. And so the 32-bit number is 4 bytes. And so if you've got a 4 stored in 4 bytes, one of the bytes is 4, that's the lowest place. The other 3 bytes are 0, which is actually a null character. So it'll stop on the very first one with strcpy. So you've got to use memcopy instead. Okay, you can figure out how big it is. So sorted numbers here takes the number of numbers, the array of numbers, and the length. So the place you need to allocate is len integers. And so that's another way people get into trouble with this. If you are using memcopy and you say that for n there, you say the number of numbers that you have, but they're actually 4 bytes each, then you won't get the whole thing. Because you got to copy 4 bytes per number. Okay, and it doesn't really put a lot of intelligence into this. Remember, computers are not people. If you tell your friend, here's a good example. Suppose you want to order some feed for your rabbit on Craigslist, and you figure your rabbit will eat about 100 pounds of hay. And the Craigslist person offers to deliver it for you. So you say, okay, great. So you want to buy 100 pounds of hay, and it'll be delivered on your porch. But you accidentally order 10,000 pounds instead. Well, instead of asking, you get 10,000 pounds of hay on your porch. And 10,000 pounds is about 4 stacked high above the cab truckloads. Probably 5 truckloads actually, 10 per truckload. That's like, you take 3 layers, and so the truck's cab is probably about 4 inches below the top. Tailgate's open, it's going back a full 10 feet, full length bed. You're not gonna get to your house. You see, the computer's happy to do this to you. The person on Craigslist might be like, wait a minute, you live in a little tiny house, you have a rabbit, and you're buying 10,000 pounds of hay? Did you miss a couple of zeros? Computer won't ask if you missed any zeros. Okay. I think that's about that. Okay. I get hardly any questions on the last one, so we'll call it good. Any other questions I didn't cover? Okay, cool. Well, you got a week left, and so it'll let me know as things come up. Almost a week. Okay, so lab. I was going to do a lab this week, and then I was looking at the deadlines and realizing that everybody's in the middle of project 1 right now, and so it's probably not a very good time for lab. Yeah, so finish the current lab, and then we'll do something else after that.
That gives you time to grade the first 2.
Yeah, I should hurry up and do that. Okay, so we got a couple of topics that are waiting for a lab or a project. Simple kernel module, so everybody gets to practice the kernel module stuff we've been talking about. That's waiting. And then this week is tagged on the calendar as processes. And so having some content on a fork and exec or something like that ought to be coming up soon. So I'll divvy these up into some kind of assignments and then assign them next time. I might do a little revision over last semester. Last semester we had a project for the simple kernel module. It's going to be a lab, and then I realized it was going to take everybody longer than a lab, so I made it a project instead. Then the fork exec, we had one about fork bombs last time near the end of the semester. Haven't quite decided how these things will go. The course is still in transition a little bit. This is the first time I've reused the book. Normally everybody dislikes the book, and so I change books, so the class hasn't really solidified very well. Anyway, so that's up through there. I used to have a project that I liked to give everybody where you write a simulated file system, but it was always dreadfully unpopular. Even people that did a good job on the assignment told me it was a hassle and it took all weekend and they didn't like it very much. I think it wasn't as cool as they thought it should be for the amount of effort. And of course, that's pretty important. Okay, so modules. Modules again. So we inserted them last time. I'm going to talk about automatic loading real quick and whether you want it. And so you might want automatic loading. You might not. Automatic loading. So if you like to plug things into your computer a lot, especially for a laptop, automatic loading is usually favored. Plug something in, the kernel goes out and finds the module. You don't have to have it on. If you have it off, then if you plug in a new device, it probably won't work until you load the kernel module. There's also automatic unloading, and that's less commonly put in. And the thing about unloading modules, we did it a couple times up here, and we pulled the module, whatever device it was associated with, quit working. So that's what happens there. Now, if you pull out the module, you kind of lose whatever state the module was in. And so in some cases, it's like, well, we pulled the thing out and then we lost everything associated with it. But that can be okay too. You can set this up to auto clean and unload after a minute or some other configurable delay. And that'll keep the kernel a little bit trimmer since the modules are actually being pulled out. Now it's normally actually not on. So we got all these modules here. And if we came up and plugged in some other device to the computer, it would load another module, drive it, and then we pull it out, and it'll actually stay until the computer's rebooted. That's usually the way they're configured. Some modules don't support unloading, but I think most of them do these days. Anyway, unloading came later than loading. Okay, where are they found? Usually lib modules. So, lib modules. Okay. So I've got entries here, and these are tagged with kernel version numbers. You notice the version numbers are all almost exactly the same. When you have an operating system that's been here for a long time, like this one, you'll see a bunch of different versions. If you say uname-a, it'll print out what we're currently running, which is Linux version 4.4.0-134. And so that's the version right here. So So if we look in that directory, we'll see the modules for this one, CD to this. And so there's stuff related to it. There's a list of modules in there. I think they might be in the kernel directory. Okay, oh, they're categorized. Anyway, FS, file system, what do we have? Oh, they're all in there. Okay, well, anyway, so you got a whole tree of modules in there, and modprobe knows to look in the correct versions directory and go find those. So when we were doing using modprobe to pull things out and put them back in, that's where it's finding the actual files. Now these minor updates, so usually the way Linux distributions work, the distribution will be released with a particular major version number. So we go and if we don't like this chart, we'll go to Debian instead. I know the Debian chart like it, but since this computer appears running Ubuntu, and the rest of these are, and there's probably more of you using Ubuntu than Debian, we'll try it. Okay, so, oh, I just want the Ubuntu with it. Yeah, I want an actual.
Take it you prefer Debian over Ubuntu?
Yeah.
Why is that? Just been using it longer, or is there something
I'm over
conventionally
it
different about it?
Ubuntu has more up-to-date software that often functions in a less correct manner. Debian trails the versions by a bit more to try to keep everything more working.
Cleaner.
Yeah, I've occasionally run Ubuntu if I bought like a new motherboard and the Debian version is too old to include proper support.
Well, it seemed kind of counterintuitive initially for your statement being like, well, since it's modern and up to date, but it isn't necessarily doing things correctly, I'm thinking to myself,
Oh, it just takes a while to get the bugs worked out.
Yeah.
My dad never liked to buy the first model year of any car. And the funny thing is, at one point, we didn't have anything with first model years. We had like 3 vehicles in there all the first model year, because, you know, whatever was a deal got precedence. So like one of ours, the 1984 Ford Tempo, and it was the only year that came with a carburetor, and it was problematic and it was backfiring all the time. And it ditched it the next year for fuel injection instead of debugging it and getting it right. Anyway, okay, so these are released with a kernel version, and they have a major version that's kind of associated with whatever release it is. So we're running major kernel version 4.4. And I think we're running 1604 LTS. And you see we could probably be updating these things. If you ever have a dull moment, they could run 1804 LTS at some point, Bionic Beaver.
those are some awfully, like, you know, zany names here. I mean,
Yeah, they try to pick an unusual creature and an unusual adjective just to support them.
Cosmic cuttlefish.
Right. Yeah, and like for P, you know, you'd think it would be penguin, right? The Linux mascot. How could they avoid it? But no, pangolin. Penguins are too common. Okay. We're on version 4.4 here. I saw Chris a little bit ahead of us, running 4.9. It's been updated more recently. These LTS releases on Ubuntu are supported for much longer. And so we kind of favor the long-term support releases here, since we don't have to change quite so often. This is the end of support date. And so our long-term release is actually supported until 2021 with updates and things. So we don't really have to update. We've got a couple of years on that. Not that many years.
no,
2020 is coming up.
it's right around the corner, realistically.
I always kind of think of it as like, you know, in the future. Well, yeah, but not very far. Yeah, where's our flying cars, you know? So then, you know, this next release will be supported until 2023, and of course, it only came out last April. Ubuntu has this fixed release schedule every 6 months, and that keeps it very up to date because every 6 months they release it. Debian, on the other hand, Debian version history. Okay, so currently we're running Stretch, and we were using Jesse before that. Before that was Wheezy, and then Squeeze, and Lenny, and Etch, and Sarge. All the names are from Toy Story. Anyway, so the stretch here was released in June 2017. But if you look at the time between releases here, they actually go for quite a while. Jesse was current for just a little over 2 years. So it's not the every 6 months release cycle with Ubuntu. The other thing is, if you look at it, there's no consistency as far as when. Yeah, so you got March, August, July, June, April, February,
Yeah, but they're
again.
pretty consistent to 2-year jumps.
Yeah, it's about 2 years. If you look down here, they got sort of a visualization of it, and you can see it's around 2 years. We were with Woody for longer than that, but mostly, yeah, about that.
Yeah, give or take a little.
The typical Debian philosophy here has been to release it when it's finished. So if we look at Debian release status, Debian release, is this going to be the right page? No, that's not the right page. Bugs, maybe that'll find it. Okay, I think that finds it. Okay, so all the history. So this is the number of release critical bugs in the Debian Linux version. And looking at this, oh man, thousands of bugs. Oh yeah, sorry. So what happens? We got 3 different lines in this graph. They've actually changed the colors since the last time I looked at this. So there's the total number, which is in purple there, and there's the number concerning the current stable release and concerning the next release. So if you look down at this thing, you can see the next release goes down. And so they insist on having that low enough before releasing it. And so if it's not low enough, and then, it would be normally time to release, so well, maybe it's not going to be released for another few months. Since it's not a commercial product, they don't have investors banging on their door and saying, why are you not making enough electric cars? So it's no big deal there. They can wait until this number is satisfactorily low. And of course, you can jump to the testing release anytime you want. So if you're looking at that and say it's this point in history, and you're like, well, they're kind of intermingled. I mean, testing is about the same number of bugs as the current release that I'm probably running. Sure, I'll just jump ship and go to testing. Yeah, you can do that. How to make your own decision there. Now, and sometimes the releases involving testing are more critical, because when they're released, you tend to see a growth in the number of bugs after it comes out. So the blue there is the current release. And so you'll see, this one was released, and then the number of bugs grows as people find them. But this tends to mean it was ones that were found later, and so they're usually less critical. And they're still tagged as release critical, but maybe they're less important somehow. Okay. Now by the end, they usually get it kind of worked out at some point. Okay. So that's version history and whatnot. So kind of a little bit of a tangent there, but I realized I hadn't explained these version numbers at all. So Ubuntu's tag uses this 4.4 kernel here for this current release. They're probably never going to leave the 4.4 line with whatever this is, Xenial or something. Anyway, and so they continue releasing minor additions and security updates and whatnot for that branch. So the kernel version history is way more complicated than just a line. You've got the major release line, but then for each of the major releases, you've got other versions that kind of come off it. It's like a comb that grows. So the spine keeps growing, the major releases. You end up with all little tooth things from the comb. Are they tines on a comb? I don't know. Maybe tines was a fork. Okay. So you got all these tines that continue off it to some point. So there's maintainers for different branches. We go to kernel.org. They maintain the Linux kernel. You can see we got the main line, which right now is at 4.19. That's what they're working on. Then we got a stable one is 4.18. A stable one is 4.17. And then we got long-term releases that are continued to be maintained, including our 4.4. And typically an LTS release will be centered around one that keeps going. So like on Debian, I think we're running 4.9 on Isoptra. And then on this one, on our long-term support release, we're running 4.4. The distribution maintainers usually will try to avoid a long-term, not using a long-term kernel for a long-term release, because if the kernel development team stops supporting whatever kernel is on their operating system, then if a security vulnerability comes out, the distribution maintainer is going to have to fix their own kernel. which a lot of times we're just not really that equipped to do. So that's where you go. See, we're still maintaining ones as far back as 3.16. And some dusty closet somewhere, I'm sure there's a server that's got Linux with a 3.16 kernel ticking away. Nobody wants to update it because they're worried they'll break it. And it's been working fine for years. And you can see that the latest release in that line was actually 6.16. So it's not just, maintained in principle. They actually release things occasionally on that. Probably had to do with security vulnerabilities and whatnot. Those are usually patched with
It's kind of interesting that 3.16 is still maintained, but 3.18 is EOL.
End of life.
Yeah.
Yeah, it could be that there's some reason for it. Maybe no major distribution is using a 3.18. Maybe there's like a old stable Debian or an old Slackware release or something on 3.16. There's still a lot of these taken away. They'll allocate resources in ways they think make sense. So these all have version names too. So list of Linux. Now, the difference between the Linux kernel names and the distribution names is that these are mostly not seen anywhere. And Linus just makes these things up in the middle of the night when he's working on something. And he changes the release name when he feels like it. So you see, it doesn't necessarily make any sense on the version numbering over here. So it'll just be that like some evening, Linus is like, hey, let's rename it. Now it's going to be Sliding Snow Leopard. And that becomes the next one. Anyway, Jeff thinks I should change this, but to what?
He wasn't feeling very
Holy
creative.
dancing man,
I don't know. I kind of like the R matey followed by the air matey.
A hurry to you. Right?
Yeah.
He was probably up really late and really tired.
Oh, please tell me that the funky weasel is jiggy with it was in the 70s.
Well, no,
Probably
that
not.
was the 70s. That was 2.6 release. This is like early 2000s.
Oh.
Man-eating seals of antiquity.
Yes. Sheep on man.
Right. You can see why these aren't usually put front and center. Like, okay, Linus made it out. Let's go.
Dive Master Edition, Linus's diving activities.
Now, what are we on? So 4.3 to 4.6. We're on Dory Fishbowl.
Her sheep internet hole.
Windows for Workgroups was kind of a big release. It was about 20 years before Linux kernel 3.11.
Linus sounds like a hilarious individual.
Yeah, or something like that.
Well, they say genius is next to madness, so if he's extremely eccentric, I
I read
guess.
this article once of an interview with Linus Torvalds himself and the Free Software Foundation, or maybe it wasn't them, some other contributor had just sent him an espresso machine, like a fancy one. They make these things. I don't know what model it was. Rocket makes ones. Here, there we go. Just go straight to one exactly. So it'll show up as a background eventually. Apparently, our internet's slow today. So they just bought him some fancy espresso machine. I don't know what model. We'll say it was something like that. And it was a very expensive one. And I think they figured that it would actually work out in terms of lines of code per dollar and all that kind of stuff. So when they interviewed him, he was making repeated shots of espresso on his espresso machine, trying to figure out if it had a metallic taste or not. Apparently like 20 or 30 in a row or something. Is this right?
Whoa.
Apparently him and the interviewee who was being given like espresso shots, like, does this taste all right? We're both very caffeinated. Anyway, okay, so that's kernel version numbers. Okay, so back to where we're going. Let's back down. Yeah, so Linux kernel modules are all in slip modules and have to be carefully set up for the right versions. So versions, I wasn't totally off track. Kernel version has to match the module version. And so as the kernel changes, this is one of the reasons we're sticking with a major release path. Typically, the major releases, like if you went from 4.4 all the way up to 4.9, you might have changes that actually make modules no longer function. Because you can change where things are inside the kernel. You know, you can have some symbol that's either deleted or it means something different or something like that. So the module does have to match the kernel version number. Now usually there's not that big a deal. I have had times before for this exact class where I wrote a kernel module as a demo in my office, and it's worked great on whatever version I'm on Debian, and I bring it up here and it doesn't work. In most cases back then, I was on a previous release, I was on Jesse, and so I was running an older kernel version when we were using up here, and I would accidentally use some symbol from inside the kernel that had gone away. So it does definitely happen. So the modules are tagged with what version of the kernel they're supposed to work with. Besides just having to maybe have source code changes, they typically have to be recompiled to match the exact memory layout of whatever kernel version they're using. And this can often be skipped if you're using, 4.4.0-132 instead of 4.4.0-135. That's oftentimes similar enough that everything's fine. That said, the NVIDIA graphics driver will typically refuse to load if it's not compiled, doesn't have its interface module compiled for the exact version that you're running, in order to make sure it matches up there. Okay, now you can insert the module with the -F flag and force it to be inserted if you think that maybe nothing important changed, and then you'll find out if it did. If it does, you may actually crash the system, but if it doesn't, then everything's probably fine. So there's symbols that are exported to modules, they have versions associated with them. Now the compiler version also matters. And the reason is you're compiling together two halves of the same program. I might sneeze in a minute. And so if you change compiler versions, then it might change things relating to memory layout. I think it was this class where I showed you we made like an int A, int B, int C. And they appeared in some order in the final version, but it wasn't necessarily the order we wrote them in. So if you take a different compiler or a different version of the same compiler to compile your module compared to the kernel, it might have made a different decision somewhere on a memory layout that causes a problem when you try to mash them together once they're all compiled. So typically you have to use the same one. So on the NVIDIA module again, it will check and see which version your kernel is compiled with. And if you don't have that version on your system, it will ask you to install it before you install the NVIDIA driver. If you're using the package manager, of course, all this stuff works out. So multiple kernels, that can cause a little bit of an issue. Sometimes people do have multiple kernels installed in their system. If you just got a regular system like this where you boot it up and do things with it, you probably don't need multiple versions. That said, typically the operating system update mechanism doesn't actually clear out the old kernel versions. And so a number of times people have come to me and have said, I wanted to update my operating system, and it's telling me that I am out of space. If you look at your root directory, it's probably got a place called /boot. And this is where the kernels are actually held. There's a few pieces that the kernels produce when they're compiled, and so you got the pieces in here for all the versions. So if we looked at just 134 ones, we could say graphical 134, and there's your list of pieces. Anyway, so these things all appear in this directory. If we do df-h and look at how everything's set up on here, we got file systems at dev and run and / and whatnot. And so there is no separate /boot partition, and so this can grow as big as it wants to. However, in certain others, I think I have Nimrod set up this way. I have a /boot partition. And so the /boot partition on here, it's only 179 megabytes, and there's actually 127 full. So if I were to have enough old kernel versions installed in here, it would fill up that 180 megabyte partition, and I'd get an error about being out of hard drive space on /boot, even when there was more hard drive space in other places. And then you just have to go and clear out some of these old kernel versions. You can see I've started to develop quite a few.
Where's the allocation defined for that space?
Well, this is a separate partition, so.
No, we're talking actual hard drive partition.
Yeah. Yeah, if,
Not
yeah.
like something virtualized or just,
No, it's not virtualized or anything. So this is my partition scheme. I got the hard drive partitioned into 4 partitions. And the first one up there, dev_sta1 is /boot. Shows up as 190 in here. Then this is my system partition. These types over here are detected completely wrongly, by the way. And then we have /home, which is where all my files are stored. That's the biggest one. And then I've got an extra one. And the reason for the extra one is if I ever put a second operating system on Nimrod. I thought about putting FreeBSD there a number of times. Haven't done it. Part of it is I hate turning the system off because I use it all the time. Okay, so that's /boot and where these things go in multiple versions. Now, if you're developing stuff, then you might want multiple versions, especially if you're using like a kernel version is not fully stable, and you don't really want to use it for your regular work. Okay, symbol licensing here. I showed you the symbol licensing stuff with the viral GPL already. Okay, booting without the device drivers. So, just thinking about what you can have as a module and whatnot. This is, you can boot without most of the device drivers, actually. For example, you don't really need a mouse boot driver to, a mouse driver to boot up. But you do need to be able to at least address hardware gadgets on your motherboard, like hard drive controllers and whatnot. So you can't go completely device driver free. Now, the loader can throw stuff into RAM. So BIOS actually includes some basic driver functionality for a lot of your hardware. Basic input-output system. It can treat your video card like it's from the late 80s, and your video card is actually okay with that, even if it's a 1070.
so you can get up and running. A lot of newer motherboards have USB mouse support too, which is nice.
Yep. So it's got some basic device drivers in the BIOS, and so it's possible for some stuff to get loaded into RAM before the kernel starts. The very first thing that runs before the kernel starts is the bootloader. And so on this one, we're using Grub. Grub is a successor to Lilo. Lilo, Linux loader, it's actually what I'm still using down in my office, even though it's been obsolete for about 15 years. Lilo can load Linux and it can load Windows. And so it used to be something you'd use for dual booting. Eventually it was replaced by the more modern Grand Unified Bootloader, or Grub. And Grub can boot about anything you want, including BSDs and other operating systems. Grub also supports reconfiguration just by changing some files. And Grub will let you go look inside partitions and search through files and all kinds of stuff before you actually boot your operating system. Includes some basic device driver support for a few things. Anyway, so Grub is pretty fancy. I was having some problem with it on my computer downstairs, and I was just like, I knew how to fix this problem, 15 years ago. I'm going to install Lilo. Problem was fixed. I realize that that's a little bit like taking your car and being like, man, I just don't understand these computer things, and dragging a carburetor out of your shed, pulling it onto the top of your, 2008 Civic and having it start working.
I like a carburetor.
Yeah. That's okay. Still got 100% file system. So insmod, I showed you the init module already inside there. Let's actually go switch ahead to /proc just a little bit here. Okay. So I think I have another kernel demo here loaded on this computer already. Crypto. Hey, there it is. Okay, I got this crypto services module. Go ahead and rebuild it. To services.ko. Okay, I kind of forgot what it does. Okay. Oh yeah. So this makes a file in /proc file system. I knew it did that, but I forgot what it was called crypto services. So the /proc file system, we go over there. This contains pseudo files. They're not real files, as in they're not on your hard drive and they're not taking up space. And so basically they allow the you to call functions inside the kernel and interact with it. So for example, if we cat CPU info, I do this a lot in Linux class, you can see the CPU megahertz down there, 1206 for this processor. These days, unless you tell them not to, CPUs ramp down to a low number of megahertz normally in order to save power, which makes your computer quieter and your laptop battery last longer and all that kind of thing. But if you're like, well, I'm tired of waiting for it to come back up, you'll get a little bit snappier response this way. You can tell your BIOS just run the thing full tilt all the time. So
Kind of diminish the lifespan everything.
right. Anyway, 1,206.691. Hey, look at that, changed. The fact is, there wasn't a file that changed. What happens is when we try to print out this file, there's some function that's called inside the kernel, and that function goes and collects the information for us and produces this chart, and then it returns it like it just came out of the file. So it's sort of a pretend file, and so that's why I can change anytime right there. Okay, if you run it a bunch of times in a row, it won't change that much. You might say, hey, can you make it get a bigger number? Sure. We just got to get us into view. Okay. Oh, it's probably not that one. So the problem here is it's got a bunch of cores. So I'll go ahead and do that. So there's a display where they're all running. You can see they're all going about 1200. Okay, we won't bother to save that. We just made it do all that work for nothing, and now we're going to do it again. Okay, so see, two of our cores are actually ramped up
a little.
Yeah. And, oh, I was done. Still about done. Okay. So again, we don't want to save that thing. Okay. Okay, so looking into this file here, it's got a proc file name of crypto services, and it does make that file. We'll take a look at it in a minute. But the big point here is to be able to call these write simple and read simple functions that are going to be inside the kernel. And so remember the struct file operations. We keep talking about the struct file operations, and I keep showing it to you in the ext4 and whatnot. So here's an example of making our own struct file operations. So for our file, read means, if you just want to read the file, then you run the read simple function up there, and write means we run the write simple function right here. Now those have to take a very specific set of parameters, and the parameters are kind of structured to read from actual files, but they still work fine for what we want. You have a struct file pointer, which is a set of information that describes your file. We've got a buffer there, a char star buffer, and so this is the address of a buffer where what we read is supposed to go. So we'll copy everything into that buffer. And we've got a count, that's how many characters we should read from the file. And this is a maximum. So if our file wasn't big enough, we wouldn't read that many characters. In this case, we're going to write however many we write, and that's that. And then it's got an offset into the file. How far into the file do we want to start reading? Which we completely ignore, because it's not a real file. You can't have an offset into it, really. I suppose you could use that parameter for something. It gives you a number in your file, and so if you needed one of those for something, sure. In fact, you could use it for your file, and say we were doing this with CPU info. They could have set that up some CPU info. If you say, oh yeah, my offset is 100 characters, but it's like skip the first 100 characters of the report and start dumping it into user space. That'd be fine. Do that. Okay. So let's get this readout and not readout mechanism. But I'll look at write here real quick. So same kind of thing. I've got a file pointer. It's a const char here now, this user space buffer. The reason it's a const char, this is the information the user expects to put into the file. So we're not expected to change what they are about to write. And so the physical sense, I suppose, if you ask somebody, oh yeah, can you write that down for me, and hand them a blank piece of paper, you expect they're going to write on your paper, right? But if somebody's like, oh, can I borrow your notes a minute? You don't expect that they're going to erase them for you, right? So that's kind of the way this works. Right here, we're going to take the information from the user without erasing it, and we're going to do what we do with it. So then this count, this is how much stuff is in here for us, and then the offset, like where does it go into the file? Because you can put stuff further into a file if you don't want. You don't have to put it at the beginning. Okay, so that's the parameters on this thing. And then the way they're set up here, we have this struct file operations, and so we set read and write in there. And then we have the init and cleanup functions, just like we do to the blinking kernel module. And so we got to print K there to just say, hey, we're in the kernel. And we'll create a file in /proc. it'll be proc file name, that was crypto services, and it's got a few parameters, but the really interesting one on here is the proc file operations. So this is the address of this structure here, very much like Project One. Well, Project One was contrived to be like this. Okay, so there's where that goes into the proc there. And then when we clean up, we actually just remove the proc entry. We don't need it anymore. This one's licensed under GPL, and the kernel is very happy when he licenses things GPL, so I went ahead and did that, which means that anybody can have my code here. Okay, so looking at the way what this actually does, this is an encryption module, and so you give it something and it encrypts it and holds it in kernel memory until you want to pull it back out. So it defines a buffer up here, and the buffer is actually pretty big. This buffer, 1024 squared gives you a megabyte, and in general you should avoid allocating megabytes in the kernel, but it was an expedient way to do memory allocation for this little demo. So then we have this readout mechanism. Here's the reason. So if you suppose you're in reading from this up in user space. You might say, go ahead and read from this, and here's my buffer, and my buffer is a gigabyte, and so you say that in count, and you give an offset of 0. And then you get back some amount of information, read returns. So if we look at read, this is the read you would call in order to run our read. And, there's a different version that has the offset in there. Anyway, so this, when you give it a size t, it reads up to that. So on success, the number of bytes read is returned. 0 indicates end of file. And a file position is advanced by this number. But it mentions here it's not an error if this number is smaller than the number of bytes requested. This may happen, for example, because fewer bytes are actually available right now. Maybe because we're close to end of file, or because we're reading from a pipe, or from a terminal. So if you're reading from a pipe or a terminal, if you pipe something into something and output goes through as it's produced, the terminal waits for the keyboard. It could also be a network socket. If you call read on a network socket, you can read over the network, but reading will happen at whatever pace you actually receive stuff. If the sender doesn't send anything for a while, read will return and give you back a count. But of course, there could be more stuff on the socket later. So you might want to call read again. So common utilities that print files, if we say cat cryptoservices.c, cat prints it out. But the first thing cat does when read returns is it calls read again to see if there's anything more that it ought to print out. And so that's why cat stays open if we give it a pipe read from. If we say cat, so if we say cat like this, we just say stuff, cat pipe that into cat. Okay. Now the second cat is there is waiting for anything from the first one that might come through. So anytime something comes through, it's ready. So it just calls read again, unless it detects an end of file. An end of file is because read returned 0. Okay. So back on the inside, which I think I just closed.
They have like a natural timeout in there, like, I don't know, like after 45 seconds and no response from the user, it'll back out.
Oh, cat won't time out. You can leave cat running like that for days.
That's kind of, I never tried, but I was just curious.
Yeah. So if you run something like cat and cat the file, cat will call read, and you give it copy to you go ahead and copy to user the stuff that we want to copy to him, which is actually our encrypted content that we're storing in a module. And then we set read out to 1 because we know that cat's about to call this thing again. And so if read out was set to 1 and we just read out something, we'll say read out is 0 and return 0. 0 bytes read. That indicates the end of the file. So that will stop cat and things like that. So if we go to the file, we go to /proc, and so it should be there as crypto services right there. Echo gerbils don't fill up spaces very well unless you have a lot of them. Okay, put that into crypto services. Oh, we have to do that. Okay, we'll try that through. Okay, so it went into crypto services. So now if we cat crypto services, there is the encrypted version. Yeah, And actually, if we echo the encrypted version in, into cryptos. I don't know what's going wrong there. Oh, it's got a quotation mark in it. Quote that like this. That'll take care of it. Okay. If we do all that correctly. Hey, there we go. We decrypted it. We can use our crypto services module like that. Okay. So let's go back to here and look at this thing. Okay.
I wonder how the encryption works if it's running off of something like the timestamp or something, because it's not like you're handing any parameters or delineators when you're trying to decrypt it.
So here's the encryption. So we start with, we make an int I up there, and we copy the buffer up there into our buffer, that buffer right there. Just spring copy it. You can do that. Then we set the end of our buffer to a null terminator to make sure it's null terminated. I don't remember if strncpy copies the null terminator or not. Apparently I thought it didn't when I wrote this. So then we put this in print, we print case, so you didn't print out that log there. And we do this loop here. And so when we go up to the count here, we're going to increase I by 1. So if it's uppercase, that is, if the ASCII value is less than 90 and it's above 65, then we go ahead and add 13. And if it's higher than 90, then we subtract 26 to roll over at the end of the alphabet. Same kind of thing for lowercase. So by shifting 13 places, when you encrypt it again, it gets decrypted. So there's 26 letters in the English alphabet. And so if you shift 13, then you shift 13 more, you're right back where you started.
So it's a Caesar cipher.
It's a Caesar cipher with a shift of 13. Yes.
Interesting.
Yeah. So then it just keeps that in the buffer until read is called for any of this thing. Okay. So this adds to the encryption algorithms that the kernel supports. The kernel already supports encryption algorithms. If we, so we're here in proc, right? Here in proc, cat crypto. These are encryption algorithms that are supported inside our kernel. The kernel will do them for us. So there's a lot of old favorites in here, like AES. And we've got a couple different things we can actually do with AES in here. But none of these is a Caesar cipher. So we made a module that adds it as a kernel-supported encryption method. That's what modules are for. You can add stuff. You make it better. The more cryptography algorithms they support, the more secure our kernel is.
Makes sense. Gives you more options.
Yeah, it's good to have lots of options. And if they want to brute force which encryption method we've used, it'll take them one more try. Okay, anyway, so yeah, it is a silly module. It's just to demonstrate these simple and right symbols. So that's what happens. Now, I haven't specifically defined the terms user space and kernel space, but we're definitely dealing with them right now. So cat, where we were printing stuff out, and the redirection into kernel both operate in user space. User space includes everything that's not in the kernel. So if you look at the processes running on the system, they all run in user space. And so that even includes ones that are only available by root, because root is a user. And so whatever root is running is a user process. Yeah, so the whole process is, user space versus kernel space is independent of the Unix permissions here. So that's everything that runs on the user space. So if we look at man read, where we're looking at this, this is the user space end of the read operation. The user space program calls this function read, and then it can read from files. And so what we're seeing inside our kernel module is the kernel side of things, the kernel space side. And so that's where the read comes out. So just like with the ext4 operations, any of the files in the system are going to have a FOPS structure, a file operation structure associated with it. So when you call read in user space, the file operation structure will be found that you're trying to read, and then its read function will be called. And then you get to read whatever it is from that file. So that's the distinction here, kernel space versus user space. Anytime you go between them, it typically requires an interrupt, where you interrupt what the CPU is doing so it can drop into kernel mode and take care of the kernel's request. So usually if you can do something, if you have a choice of where you should do something, you should probably do it in user space. The kernel cryptography algorithms, doing it in crypto space can make things, or doing it in kernel space can make the cryptography a little bit more secure in some ways. Partly because then everybody doesn't have to implement the algorithm on their own, but also partly because when it's in kernel space, it makes it very, very difficult for different user processes to spy on what's going on.
Yeah, it's hierarchy. They don't have access. So.
Right. So the kernel is kind of below the whole Unix permissions thing. The Unix permissions thing does not apply to the kernel. Permissions really don't apply to the kernel. It operates the CPU at a basic level. It's got the permissions. It doesn't need permission. Maybe that's a better way to put it.
Yeah.
It is the arbiter of whether something has permission or doesn't have permission. It is the janitor. You know, the janitor can access everything, right? Yeah. Yeah. Okay. So, and the janitor does unglamorous work behind the scenes. It's very important. So actually, they're very much like operating system kernels.
Without the cleanup, everything would just become cluttered and then crash.
And a lot of what the kernel does is clean up used memory areas and things. Reallocate it for other uses and stuff like that. So that's user space and kernel space. That's why everybody's very concerned when there's a rootkit or something like that, or a virus installs a rootkit, because then it's below the level of permissions.
And at that point, antivirus is just out the window.
Right. It's the arbiter of what the antivirus can and can't do. Yeah. Okay, so I think that's about it for today. We'll talk about processes next time. I put them in notes for this time, but without a whole lot of hope of actually getting there. So cover those next time, and what the operating system does and that kind of stuff. Okay, well, we'll see you all next time. Have a nice week. LCS 101 class is starting to gather outside.